In this video, we're going to utilize what we've been using in finding the limit as h approaches 0 for any given point to find instantaneous velocity. So what we're really doing when we're working with limits is that on a trajectory, we're going to say that at any given point, and we will just simply say that this trajectory goes on and on and on, and it is a negative slope as it's traveling from a higher position to a lower position. We're going to find that it is a negative slope, but the velocity itself is not negative necessarily. It's obviously, it has to have a positive velocity. It can't be traveling negative feet per second. So in this case, we're going to still utilize some of the same variables so that this makes sense. And we're going to say that this is an expanded or magnified view of a given point on that trajectory. So we're going to say that this is essentially expanded, and that we have t sub 0 is the point, and then that little bit of t sub 0 plus h. So we are given that we want to find the instantaneous velocity at 5 seconds. So we know that t sub 0 is 5. So what we're going to do is essentially just the same steps that we've been using, which is to first let's find out what then s at t sub 0 would be. We can write that here. S at t sub 0, we would then have s at t sub 0 plus h. And we know that t sub 0 is 5. Therefore, we can say that s of 5 is going to be equal to 500 minus 16 multiplied by 5 squared. So we can solve that down. And of course, it's going to be 25. It's going to be 500 minus 16 times 25. And I have 500 minus 16 times 25 gives me a nice even number of 100. So this is 100. So s for t sub 0 plus that little bit h is going to be equal to, and we know that t sub 0 is 5. We have that, plus that little bit of h will therefore be 500, will therefore be plus h equal to 500 minus 16 multiplied by 5 plus h squared. All right, well, let's walk through that 5 plus h squared. So we're going to FOIL, and we will end up with 5 times 5 is 25. We're going to say 5 plus h, 5 plus h, and then we'll end up with 5 times h plus h times 5 gives us 10h, plus h times h is h squared. I always like to write this as the greatest exponent to smallest. So that's what we end up with there. Let's go ahead and finish solving this down and reducing as far as we can. So we'll have 500 minus 16 times h squared plus 10h plus 25. And we can further reduce this. So we can carry our 16 through, and we will end up with 500 minus 16h squared. Negative 16 times 10h is going to give us minus 160h. And negative 16 times 25 is going to give us, let's see here, negative 400. So we have solved for both of those, and utilizing our difference quotient, then we can go ahead and substitute that in. So the next step then is just to go ahead and create your limit functions. We're going to have the instantaneous velocity, and that's going to be equal to, as the limit of h is approaching 0. So as h approaches 0, and we'll go ahead and put this in. So remember, and I'll set it up again for us so that we're going to have s of t sub 0 plus h minus s at t sub 0 divided by h. And we'll go ahead and put in what we have so far. So s at t sub 0 plus h, we figured out, was, and we can further reduce this, of course, we have 500 minus 400, and that gives us 100. So that's minus 16h squared minus 160h plus 100. All right. So we can go ahead and bring that down. So we'll end up with negative 16h squared minus 160h plus 100 minus what we found out for t sub 0. S of t sub 0 is 100. And of course, these points have been set up so that we get a nice number, or a nice rational that we can reduce here and simplify a little easier, just to see how this works. So the limit, as h is still approaching 0, and until we plug that 0 in for h, we want to continue bringing that limit down to designate what h is and what we're actually trying to do. So we end up with minus 16h squared minus 160h over h. Now at this point, you could do a couple things. You could go ahead and so you could just factor out from each one of these terms. So I just want to show how this actually looks. So if we have this split apart as just a standard fraction, we would have 16h squared over h minus 160h with that same denominator. And you can easily see it now that you could reduce such that this is negative 16h minus 160. That would be fairly easy to see this way. So without splitting it apart, though, you can see that for each term in the numerator, and of course the denominator containing just h, we can reduce this. We can reduce this and rewrite as the limit of h as it approaches 0 is now going to be negative 16h minus 160. There's another way you could do that. Of course, we could take, at this point, we could take this and say that negative 16h squared minus 160h, and for the numerator, we could then factor out that common h. So we could bring that h out. And in doing so, we would end up with h negative 16h minus 160 divided by h And as you can see, we end up with the exact same thing. So there's several ways to do that, whatever's comfortable for you. But as you're working with a long string, you might want to get in the habit of just kind of seeing what each term contains and what you might be able to factor out of those without expanding this and creating yourself a longer process. So from here, of course, we do not have an h in the denominator. We no longer have restrictions that would cause division by 0. So we can go ahead and put 0 in, substitute 0 for h, and we will end up with minus 16 times 0 minus 160, and that will give us our negative slope and 160 units, whatever that might be. It could be 160 feet per second, such that, as we saw above, I created that negative slope such that an object is really falling at 160 feet, let's say, per second. And of course, this tells us that it's falling and not a trajectory, and not a positive trajectory. So I hope that helps, and thanks for watching.